Thank you. Thank you very much. So today in my talk, I will bridge some of the work that we've heard this morning and yesterday. So I'm going to talk about hierarchical Bayesian models of psychosis, linking precision, prediction errors, and cortical disinhibition. So as Sorenza said in her lovely introduction, I'm also hailing from the KCNI, similar to John, so at the Krembil Center for Neuroinformatics. And there I'm leading the cognitive network modeling lab. So basically what we want to do in the lab is bring participants in a certain cognitive state in which we can better understand how certain symptoms emerge, such as delusions, for example. And to do that, we use computational models of behavior. So active inference models, hierarchical Gaussian filter, reinforcement learning models to design those gamified tasks so that we can, with minimal duration and trial size, examine those latent causes of changes in learning and decision making. And by integrating neuroimaging techniques such as functional MRI or electroencephalography, we can address the implementational level. So how does the brain change as we change our beliefs, as we change our decisions, or as we change the way we sample the world? We're particularly interested in changes in synaptic plasticity so that we can address with EEG, but also changes in effective or directed connectivity between particular brain regions or cognitive networks that underlie learning in specific tasks. And the focus of my lab is to direct these computational efforts towards prevention of severe mental health outcomes. And one focus of our lab is in psychosis prevention. So preventing psychosocial decline or emergence of psychosis in individuals at risk. And we've heard a little bit about psychosis, about delusions and schizophrenia in the previous talks. And here I will focus, but perhaps on the early stage, so in individuals at high risk who may or may not develop delusional conviction or may not transition to psychosis. So almost 20 years ago, I think, I had the privilege actually of volunteering at CAMH as just coordinating a fine arts project in the evenings at a early psychosis ward. And there I had the great privilege to hear stories from patients and also see their different artworks. So for example, you could, and what inspired me and what surprised me a lot is how different these stories were, how different the art that patients produce. So I was struck by the fact that you could speak to a patient and they would report, my senses are sharpened, sights and sounds possess a keenness that I've never experienced before. While another patient might say, I had to make sense, any sense, out of all of these uncanny coincidences. And I did that by drastically changing my conception of reality. So as evidenced by these two testimonials, one might argue that, yeah, there's a lot of heterogeneity in psychosis, but potentially also this is a disorder that progresses in stages, where each stage is marked not only by a change in the frequency of symptoms, but also the quality of the symptoms and the severity of the symptoms. And in the recent, in some of the recent sort of publications looking at help seeking and psychosis, many have found that the emergence of psychosis spectrum symptoms, which are not indicative of frank psychosis, but are sub-threshold and they're transient. So they're not necessarily, stable over a certain period of time, that they are a harbinger of poor outcomes in the future. So they're associated with increased comorbidities, increased risk of suicidality, and recurring hospitalizations. They might not lead to transition to psychosis, but they are harbinger nevertheless. Additionally, the majority of individuals that come into the clinic reporting reporting symptoms and obtaining a diagnosis of first episode psychosis, they have been help seeking before. So they have sought mental health services before various different moments in time. So we need more reliable biomarkers for addressing not only the changes in symptom severity, but exactly those poor functional outcomes. And of course, when you look at how schizophrenia is diagnosed by the presence of at least 2 of these symptoms listed here for at least 1 month of duration, we realize that a diagnosis might be achieved quite late in the progression of the disorder. And if we consider first-line antipsychotic medication like dopamine D2 receptor antagonists plus cognitive behavioral therapy, even though we have maybe a response rate of 60% to first-line medication and augmented psychotherapy, what we also realize is that functioning is not necessarily improving. So an improvement in symptoms doesn't mean that there's an improvement in functioning. So we see recurrent hospitalization and occupational disability. So how do we prevent patients from getting to this phase where, in spite of treatment, they're not actually feeling better? So the approach that we use to investigate this is multi-scalar. So we assess this at different levels. So first, the aim here is to relate kind of the superficial level or the top level that has to do with the behavioral, with the patient's behavior or symptom profile, how they fluctuate over time, to underlying neuronal mechanisms that we cannot measure non-invasively. But what we could do, we could use mathematical models to infer on them based on non-invasive recordings such as EEG. So in a way, we can use mathematics to develop a microscope that allows us to infer into those mechanisms. And of course, in order to do that, first we need reliable EEG biomarkers that allows us to make those inferences. But in addition, we need to design tasks in a certain way that helps us address the underlying computations, because this is when those markers are most reliable and most sensitive at picking up the mechanisms that we are particularly interested in. So I'm going to talk about different EEG paradigms that we have used to essentially bridge the computational to the cellular level, as well as linking to the behavioral and symptomatological progression in early psychosis. So Al Powers at Yale and his group have looked at the temporal progression of symptoms in individuals at clinical high risk for psychosis. So clinical high risk is a bit different than the presence of psychosis spectrum symptoms. It's actually ascertained through clinical interviews. And there's different things like genetic risk for schizophrenia that come into play, not only this occurrence of subthreshold psychosis symptoms. In the clinical high-risk population, about 30%, and in some cases that percentage is even lower, goes down to maybe 20% of those clinical high risk transition to psychosis or develop frank psychosis within the following 3 months of ascertainment. However, the large majority actually get, the large majority of those that don't convert also experience progressive decline in psychosocial functioning. So they're actually, many of them are actually doing worse in spite of the fact that they're not actually transitioning to psychosis. So Al and his team looked at, can this temporality of these symptoms, the waxing and waning, help us understand or parse the heterogeneity in these trajectories? And what he found, and this was across different longitudinal clinical heuristic data sets, Naples 3 and 2, acquired at multiple sites in the US, but also in Canada. What he found is that delusional mood that precedes hallucinogenesis, or the emergence of auditory verbal hallucinations, is associated with the greatest sort of decline or severity in symptoms. So that there's a certain kind of temporal progression where delusional mood precedes hallucinogenesis. That doesn't mean that someone who had delusional mood and develops auditory verbal hallucinations will not experience delusional mood. These are always waxing and waning, but he looked at this kind of temporal transition between those states. So the question is, what is going on computationally? So delusional mood is defined by something doesn't feel right, but I cannot quite put my finger on it. So it's not actually having a very precise delusional belief that you hold with conviction. It's something is not right. My sensations are a little bit more either feel more salient or are more dulled. Things that are really that an individual might not be able to exactly point to what that means. So we want to understand how to explain how this delusional mood emerges and how it kind of transitions to other symptoms. So for that, we want to take a hierarchical Bayesian approach. And you've heard from Carl's lovely talks this week, as well as the presentation this morning. So you know very well the models that I mean here, but the idea is that we treat perception as an active process, as a process of hypothesis testing. So continuously making predictions, generating predictions about hidden states in the world, and updating those predictions via prediction errors that reflect the discrepancy of about what was anticipated and what was actually experienced. Now, what is important here when we take this, when we consider the Bayesian inference process in a hierarchical fashion, and Christoph already talked about it this morning. But what is important to emphasize here is that beliefs change not only as a function of the prediction error, but as a function of a ratio of precisions. The sensory precision that augments the impact that prediction errors have, that indicates that that prediction error is reflecting maybe a transition in the context, so a meaningful change that requires an update in our model of the world. However, this is modulated by the higher level, or the belief precision, that reflects the confidence an agent has in their model. So in other words, this is evolutionarily adaptive because it allows us to generalize our model of the world to different contexts. And that reduces the impact that prediction errors have. So that keeps our model robust and generalizable. And it's this kind of dance, this relative contribution of the sensory precision relative to the belief precision that modulates how fast we learn from prediction errors. And the hypothesis here is that it is this very dance that between those two precisions that allows us to better understand the temporal progression of psychosis spectrum symptoms. So we might posit that the that this enhanced learning rate, which might lead to overfitting or changing one's model of the world based on random fluctuations in the environment, that maybe this is what we see in early psychosis. This is maybe what defines delusional mood, the increased precision of incoming prediction errors. But what we argue here is that it's not necessarily coming from the bottom-up precision of the prediction error, but actually driven by the precision of higher level beliefs. So higher level beliefs are imprecise, leading to an overlearning from prediction errors. That leads to a misattribution of the causes of sensory inputs, but it also leads to a misattribution of contextual changes or volatility. So we're particularly interested in using experimental paradigms that allow us to disambiguate those two sources of precision. And so you've heard from Christoph's talk about the hierarchical Gaussian filter as a computationally tractable model of individual learning under uncertainty. So here, what we see through the hierarchical coupling of beliefs that change in time as Gaussian random walks, via this coupling, we have a cause for the dynamic changes in one's model or belief precision. So we have a cause of the changes in the confidence about one's model of the world, and that is this phasic volatility. In other words, when we estimate that volatility to go up, so environmental context to change quickly, that is passed on down the hierarchy and informing our model to update and adapt very quickly to kind of meaningful changes in the environment. So via the model-based parameters that we saw determine the dynamics of these belief updates and precision-weighted prediction error updates, the key parameters that determine that and kind of modulate the impact of higher level belief precision on prediction errors might be the baseline learning rate or tonic learning rate, or it might be via the coupling between those two levels, meaning that with a higher coupling, volatility or the estimated volatility can have a stronger impact on how much one changes their beliefs. However, if we think about this hierarchical belief updating process in a mean reverting fashion, so beliefs do not only change as a function of precision-weighted prediction errors, but they drift with a certain speed towards an equilibrium point, meaning that over the course of the task, a patient might develop a certain bias towards about a certain state, and that bias can have a nonlinear additional impact on how they learn about the sensory input. So the idea here is that if you expect volatility to increase when you're presented with contextual changes or reversals, then that increased expectation of volatility will reduce the precision of your beliefs, reduce the precision of your predictions, leading exactly to this faster learning rate, higher dynamic learning rate. So this is the hypothesis that we have a reduction in top-down belief precision that leads to an overlearning from noise, basically noisy prediction errors. Now, how does that relate to the neurobiology of psychosis or psychosis progression. So this is a model proposed by Crystal and colleagues in 2017, and is the neural ensemble hypothesis. Essentially, it's a model that supports a progression, a neurochemical and neurobiological progression that can explain a host of findings in early psychosis with respect to excitatory inhibitory balance, with respect to hyperfunctional connectivity or reduced effective connectivity. And to walk you through that, the proposal is that originally individuals that go on to develop psychosis have as a starting point a glutamate synaptic dysfunction. So they have a glutamate signaling deficit that can come from can be explained by sort of local at the local circuit. So reduced intrinsic connectivity from pyramidal to inhibitory interneurons. So this glutamatergic synaptic deficit is expressed specifically on NMDA receptors, and that it's an allostatic adaptation to that particular deficit that leads to a deficit in inhibition, so a GABAergic deficit, or an imbalance between excitation and inhibition, and also hyperconnectivity when we're thinking about whole brain long range connectivity. Now that allostatic adaptation triggers a cascade of local and global changes in connectivity that also triggers this a secondary allostatic adaptation, which is synaptic downscaling and programmed synaptic elimination. So disconnectivity with the Y, right? Disconnectivity. This is a proposal by Klaas and Stefan. And what this essentially can explain is, for example, accelerated brain aging in schizophrenia and psychosis. And so in a way, the symptoms that the hypothesis, and I will quote Rick Adams here, is that the psychosis symptoms is the price the brain pays for an initial glutamatergic synaptic dysfunction. So we can think about it in terms of the underlying neural computations as the first wave of allostatic adaptation being an inhibitory deficit in terms of the gain on inhibitory interneurons, or in terms of the connectivity between inhibitory interneurons and pyramidal cells. And where in the brain would this emerge most strongly? Well, in particular, we hypothesize that the hippocampal to dorsolateral prefrontal connectivity is key. And also, based on that hypothesis, it leads us to specifically focus on a set of paradigms that allow us to disentangle and address and test this particular neurobiological hypothesis. Okay, so the hypothesis is that we have in the predrome a glutamatergic dysfunction specifically that can be local, but also involve multiple brain regions. In particular, we're focusing on connections onto inhibitory interneurons, and that in and of itself will trigger this first wave of allostatic adaptation that actually explains symptoms and functional decline in those at risk for psychosis. And so in terms of the computation, we hypothesize that this inhibition, so the first wave of allostatic adaptation can be understood as an increased perception of contextual change and volatility that reduces the confidence or precision of predictions and leads to this heightened learning rate that many have reported. Okay, so now how can we infer on these cellular neurobiological dynamics and link our findings to symptom progression? And I will argue that we can use EEG biomarkers to do so, and particular paradigms that lend themselves very well for these kinds of empirical studies. And I'll start with a simple paradigm that involves sensory learning via mismatch negativity. So this is a very simple paradigm, often called the oddball task or the mismatch negativity task, and it assesses how the brain involuntarily tracks the statistical regularity of the environment. And this has been shown across different sensory domains: auditory, somatosensory, visual. Essentially, it's related to the probability of events in the environment. So you have a repetition positivity that emerges with a repetition of a certain event, like a low frequency tone. And that regularity is disrupted by an event that varies, in some category from the repeated tone. So it could vary in frequency, it could vary in duration, or it could vary even in frequency and duration, which makes it even more surprising. So the surprise signal can be recorded with EEG in terms of the mismatch negativity, and it essentially reflects if you essentially subtract the responses to the standard and the response to the deviant, you see this negative deflection between 120, 170 milliseconds, followed by a positivity or the P300 component. And those scale with the probability associated with this statistical regularity. So the more improbable that event is, the higher the amplitude of the mismatch negativity and the P300 component. And what has been shown very reliably and robustly in the literature is that in early psychosis, there is a attenuation of the mismatch negativity component. And once an individual transitions or converts to psychosis, this attenuation of the mismatch negativity is even larger. And we see actually something similar for the P300 component in clinical high risk and also first episode psychosis. Now, this attenuation can be replicated with a pharmacological intervention, and that's using ketamine, which is an NMDA receptor antagonist. And ketamine induces certain symptoms or experiences that are akin to psychosis, and that's why it's called a psychotomimetic as well. So what we're interested in is modeling or inferring on these underlying neural mechanisms. And this is a work by Marta Garrido and reproduced by us and various groups that showed that the surprise signal is not only it doesn't only involve kind of local adaptation or sensory changes, but actually involves synaptic plasticity and belief updating across the cortical hierarchy. So from primary to secondary auditory areas to the inferior frontal gyrus. And modulates, so the presence of the deviant or improbable tone modulates the effective or directed connectivity as well as the gain in those neuronal populations. Now, how do we test the hypothesis about the impact of volatility on this or contextual change on this probabilistic learning process. So this is a paradigm that was developed by Lilian Weber. Christoph also mentioned her work in his talk, that essentially modulates the not only the probability of the tones, but it also modulates the contextual, how fast this probability changes in time. So you have phases of stability and volatility where the probability of a low frequency tone, for example, is higher compared to the probability of a high frequency tone. But this could be done for any feature or category. What we found, so this is a former member in my group, Colleen Charlton. What we found in healthy controls using the volatility mismatch negativity paradigm, we found that the volatility manipulation has a significant impact on the mismatch negativity component, but not on the P3A component. So what does that mean is that we get a stronger mismatch negativity component when the environment is stable, more determinate, and in contrast to when it is volatile or changing more quickly. And more importantly, it is the difference waveform in these volatile phases that is associated with psychosocial functioning. So again, what we want to understand with these paradigms, we want to be able to make sense of psychosocial decline in early psychosis. So we find that it is actually the difference waveform in the volatile phase or volatile condition that is what indicates psychosocial functioning in the general population in this case. So these participants were actually the healthy control group of that was the comparator group in a clinical study that we conducted in Basel. So they were matched to patients with respect to cannabis consumption, IQ, education, and all those parameters. So the other test that we wanted to examine is whether we can use the computational parameter to investigate trial by trial learning in this particular task. So one issue with the definition of the difference waveform or mismatch negativity is that we sort of choose kind of an arbitrary cutoff for the standard in terms of the preceding repetitions and the deviant. We're not taking into account trial by trial updates in learning, but we have now a computational model of learning that can allow us to actually determine the conditions, standard versus deviant, based on the model itself. So telling, in other words, high surprise versus low surprise. And then we can also look at how the amplitude, trial by trial amplitude fluctuations co-vary with these computational states that we're particularly interested in, with the precisions at different levels of the hierarchy as well as the prediction error. And what we see is that these distinct computational parameters have distinct temporal signatures. So they're all kind of convergingly, they relate to the mismatch negativity effect and the P3A component, but not completely overlapping with it either. So we see an effect of the sensory precision early in time, between 110 and 120 milliseconds. We see an effect of the prediction error itself about the sensory outcome. And then finally, we also see an effect of the higher level precision. And when you look at these pseudo conditions, I mean because they're defined by the computational model itself, they do overlap with the roving definition or the mismatch negativity definition, but not completely and differentially. So there is a value in actually using a computational framework to examine learning in this type of volatile mismatch negativity paradigm. Now, what about clinical high risk for psychosis? Because that's where we want to get. Again, our hypothesis is that we have this imbalance in the weighting of the prediction error. And we hypothesize that it is this imbalance between the two precisions that is associated with symptom severity, and it's the learning under volatility, or the reduced ability to be able to tune one's learning about the outcomes as a function of contextual change in volatility that reflects psychosocial decline in early psychosis. So for the first question, so this is work done by my former PhD student, Daniel Hauke, who's actually working with Rick Adams at UCL currently. He's doing his postdoctoral fellowship there. He did this study where he looked exactly, so using the computational framework to look at mismatch negativity across the early psychosis spectrum. So here we had healthy controls, those that were ascertained to be at clinical high risk, and schizophrenia refers to recent onset psychosis individuals. And what we see, if we use the precision weighted prediction errors to bin our data and define our conditions, we see a significant difference in the mismatch negativity waveform, where we see the greatest attenuation in individuals that have transitioned to psychosis compared to those at clinical high risk. And we see this for both precision weighted prediction errors. It doesn't have the same spatiotemporal distribution in the brain. So this is the sensory or outcome precision weighted prediction error, whereas this is the volatility precision weighted prediction error. And we see a similar attenuation across the two groups. Now, what about within individuals at clinical high risk for psychosis that end up converting or developing psychosis? Well, when you separate the clinical high risk group into those that converted compared to those that didn't convert, you see a similar picture. An attenuation of this mismatch negativity, but this is primarily observed in for the outcome precision weighted prediction error and not the volatility. So this indicates to us that there is a utility in examining the learning process using computational modeling, trial learning process, and separating those trials based on that learning mechanism, as opposed to strictly comparing standards to deviance, in particular for understanding early psychosis and conversion to psychosis. Now, we've done this work. Colleen Charlton looked at this in individuals at clinical high risk. This is in collaboration with Michael Kiang at CAMH. And what we found also in terms of the sensory or outcome precision weighted prediction error, we found not only an attenuation, but the magnitude of that precision weighted prediction error was correlated with positive symptom severity. So it seems to be an indication of particular psychosis symptom severity in those at risk. Okay, now if we take a step back, and I mentioned to you that the emergence of psychosis spectrum symptoms that are transient, they are harbinger of poor outcomes. And really, when we look at first episode psychosis and clinical high risk, we're still potentially looking quite late in the progression of psychosis. So what about if we look at even an earlier phase, so looking in adolescents and even children, reporting, reporting the presence of these types of psychosis spectrum symptoms. So this is an ongoing study at CAMH called the Toronto Youth and Adolescent Cohort Study that is led by Aristotle Diaconescu. And this is kind of one of those flagship projects at CAMH, where the idea is to assess youth between the ages of 13 and 22 that report to CAMH for mental health services. So again, 75% of those with first episode reported to a mental health service clinic. So now we want to take kind of an all-comers approach. Let's examine all youth that are seeking mental health services, and let's track the progression of symptoms, the progression of cognitive changes. And by collecting imaging and EEG, genetics, we can develop predictive biomarkers of poor functional outcomes or increases in the severity of those symptoms. And this is a huge team at CAMH. So this is the team in a nutshell. And myself and John are sort of leading the EEG arm of the Take CAMH cohort study. So it's a huge, huge endeavor and a lot of collaboration. So the target sample size is to track 1,500 youth for 5 years, assessing them every 6 months, where the imaging and biosampling is done once a year. And the outcome variables are functioning and psychosis spectrum symptoms. So I'll present preliminary EEG data that looks at this. First, you might ask, okay, how many, what are the, if we look at the diagnoses and psychosis spectrum symptoms, what is the distribution in this population? Because honestly, this is the first study of this kind that looked into this. So interestingly, based on the first 500, I believe, data that was acquired, what we found is that 49% of those help seeking exceeded the threshold for psychosis spectrum symptoms, which is quite remarkable. 44% endorsed suicidal clinical threshold of suicidal ideation, and the majority of individuals assessed showed comorbidities. So were the majority met criteria for anxiety disorders and then also depression. But we want to move beyond these categorical boundaries in terms of diagnosis, but really try to understand these psychosis spectrum symptoms, which actually can appear or disappear when people are assessed over time. So we try to understand what leads to their emergence and persistence. So this is a first examination of the mismatch negativity in this cohort, and this work is based, I believe, on 89 or the first 89 participants, and there's still a lot of individual variability and complexity that we're parsing through. But essentially, what we see in the preliminary data, similar to what we see in those at clinical high risk for psychosis, we see an attenuation of the mismatch negativity in those that meet clinical threshold for PSS. Again, binned as a function of the outcome precision weighted prediction error. So again, using the mathematical model to look at learning effects. And this is work by Malad, who's in the audience as well, as part of his PhD thesis. What we found was a very interesting effect where the expression of the precision weighted outcome prediction error correlated not with the sum PSS scores, but with those PSS scores that specifically capture delusional mood. So there seems to be specificity with respect to precision-weighted prediction error learning in terms of the symptom profile, and that is something that we want to investigate further, also using computational modeling. This is what we find, what we see, for example, when we're looking at those at clinical high risk for psychosis. So it's distinct spatiotemporal pattern, as well as the temporal correlation with the effects. Now, you might ask, well, how does sensory learning capture the complexity that we see in psychosis? It's almost too reductionist. And when you talk to clinicians, clinicians say that actually the way that a person speaks, the way they formulate, the way they describe their symptoms could be very rich and indicative of the progression of psychosis and potentially emergence of a first episode. So we also wanted to investigate, using a similar computational approach, semantic predictive processing. So this is work in collaboration with Michael Kang at CAMH. And that brings me to a different EEG biomarker, which is the N400 ERP waveform, that essentially reflects sort of a semantic prediction error. So the N400 amplitude is larger, more negative in voltage when participants are presented with an unrelated or semantically incongruent word. So every morning I drink my coffee with milk and sugar. Sugar would be the congruent, semantically congruent word, but milk and sand, if you see sand as the end of that sentence, that would elicit a prediction error. That would be unexpected. So this is essentially what the N400 component reflects. And the reason that it is studied in the context of schizophrenia, again, like with the mismatch negativity, we see that schizophrenia patients show an attenuation of the N400 component. So in a way, their semantic network is much more flexible, malleable. So they're less surprised to the word sand. Their surprise to the word sand is not as different or not semantically as distinct as potentially their response to sugar. And so Michael Kang in particular was interested in sort of controlled and automatic processing and the N400 component. So he also designed experiments where he modulated the stimulus onset asynchrony. So shortened the time for deliberation, for prediction, between the prime and the target. To look, and his hypothesis was that the longer SOA will elicit a bigger prediction error compared to the shorter SOA. And the question is, what about clinical high risk for psychosis? What he found was that, in particular, in the long SOA condition, individuals at clinical high risk for psychosis show an attenuation of this N400 component. Maybe not as large as patients with schizophrenia or those that transition to schizophrenia, but they also show an attenuation. Now, Michael went further to ask, is this attenuation clinically informative? And what he found was that the degree of attenuation was associated with a change in psychosocial functioning 1 year later. So when participants were clinically assessed 1 year later. So now the baseline is the N400 EEG biomarker detection. And he was predicting functioning 1 year later. And he found that those that showed a greater attenuation of the N400 component were worse off, more socially isolated, suffering more 1 year later when assessed. Now, the question is, what can we use neurocomputational models to understand what explains that attenuation, the N400 component, and what aspect of the neurobiology is actually indicative of psychosocial functioning? And of course, there's a plethora of research suggesting that it might be related to NMDA receptor plasticity and glutamatergic functioning that leads to this, what we talked about at the beginning, this imbalance between excitation and inhibition, where reduced inhibitory control is impacting on this delicate balance that might be associated with functioning 1 year later. So that was our hypothesis. Faster decay of inhibitory postsynaptic potentials and reduced I to P connectivity was what was responsible for that reduction in functioning, social functioning 1 year later. So we used a neuromass model approach, Janssen and Ritt, where we have 3 neuronal populations: pyramidal cells, excitatory spiny stellate, and inhibitory interneurons, neurobiologically connected. So we placed these this neuromass model in different nodes and look at both local dynamics of intrinsic connectivity and synaptic gain, as well as changes in directed or effective connectivity between brain regions. So this is a collaboration with John Griffith's group and Zhang, there he is, using the Hobbit. You heard a little bit from Mina Rose yesterday. So essentially what we want to do is we use this whole brain Janssen-Ritt model to fit averaged grand average waveforms across those 2 conditions. So unrelated and related semantic pairs at short versus long SOAs. And what we're interested in particular is how the local gain parameters can help us disambiguate distinct sources of EI imbalance. So the parameters that we're particularly interested in were the parameters, the intrinsic connectivity parameters from P to E, E to P, and so forth. And our hypothesis is that the parameter C4, inhibitory to pyramidal connectivity, would be predictive of reduction in decline. We also looked at the decay rate of excitatory postsynaptic potentials, inhibitory postsynaptic potentials, and the gain parameters as well, denoted by capital A and B, or small a and small b. All right, so what did we find? First of all, we found a group difference that was present irrespective of condition. So a group difference between clinical high risk and matched controls. And we use partially squares to essentially take a multivariate approach and consider this array of computational parameters that determine local dynamics, and look at which parameter significantly differs across those 2 groups and differs in a reliable fashion across participants. So the parameter that really stood out was the capital A, that can be interpreted as clinical high risk for psychosis individuals showing a heightened excitatory drive in pyramidal cells. And this had the relative moderate effect size and aligns with hypotheses of reduced NMDA-mediated inhibitory control. Now, we were interested, not specifically in the group difference, but identifying which of these parameters was associated with functional change. And let me go back. One of the challenges is that there are a lot of interdependencies, collinearity between those parameters that have to be taken into account. And what we wanted to do is not only use the parameters themselves as features, but extract the neural states themselves and see if those neural states can help us understand the causal underpinnings of those reductions in the N400 component. So what we found, so basically we found a significant group difference, relatively large group difference, in particular for the long stimulus onset asynchrony conditions, where we see, if we look at the neural states, we see an increased magnitude of excitatory drive very early on, between 150 and 200 milliseconds, that and reduced inhibitory controls, so faster decay of inhibitory postsynaptic potentials, that was not only driving this difference in excitatory drive between healthy controls and clinical high risk for psychosis, but was indicative of reduction in psychosocial functioning 1 year later. So more excitation and reduced inhibitory control. So actually, this effect, this early increased excitatory drive, was driven by primarily three parameters indicated here. Now, we also found in the short SOA, now this is the automatic, so sort of more automatic semantic predictions. We also found a significant group difference. And now what we found was that the magnitude of inhibition of pyramidal cells is what was significantly different between the two groups, and what was associated this time with improved functioning 1 year later. So what we found is that more inhibitory control, so slower IPSP decay, increased I2P connectivity, was associated with better role functioning. And role functioning indicates going to school, having a job. It's distinct from social, but it's also an important indicator of functional outcomes. Okay, so what these results might suggest is an indication that what we see in terms of reduction in the mismatch negativity and the N400 component is stemming from reduced NMDA receptor plasticity, specific to inhibitory interneurons, and that leads to reduced inhibition of pyramidal cells, leading to this increased excitatory drive, so input-dependent excitatory drive that is associated with psychosocial functioning. So where do we go from here? So the idea now in the individuals that take part in the TAKE-MH cohort study, what we're interested in is using these computational parameters as biomarkers in and of themselves that we can track over time and test their clinical utility in terms of predicting psychosis spectrum symptom severity, as well as changes in functioning. And we're doing the same in first episode psychosis and clinical high risk for psychosis, because we want to understand, are these mechanisms in the prodrome, in the early phases, are these similar or distinct from those that we see in clinical high risk in first episode? And because we've gamified some of our tasks, including the mismatch negativity, if you believe it, to make it more fun and engaging. We have now developed a platform with a graduate student of mine, Ore Ogundipe, the Neurofusion app that allows us to deploy these tasks and be able to allow participants to connect their EEG, high density or high density EEG, mobile EEG caps, and be able to do those experiments from the comfort of their home, so that we can actually model and look at these transient fluctuations in EI dynamics over time and be able to scale these assessments more broadly. All right, I'd like to thank my lab, the Cognimo group, and also my collaborators at CAMH, University Health Network, London, Tübingen, and Netherlands and Switzerland. And thank you very much for your attention.